All right, 9:45. Let's get those cameras on. Let's get those cameras on. I want to see your lovely faces. I want to see your lovely faces. I don't want to teach black boxes. I don't want to teach black boxes. Luke, where are you? Luke, Cameron. Ava. Patrick, yeah. Gordon's there. Josh. Okay, let's stand up. Let's stand up. Okay, how many people did a ton of work over break? Oh, that would be nobody. That would be nobody, just like me. Spent my entire break with grandsons, so I had a great break, Okay, let's sit back down. Now, Lord willing, we will all stay nice and safe. It's killing me not having you in the class. It's just killing me not seeing your faces and being back on the grid. Last time we talked about, like Dr. Warren, I don't even know. What class is this? So this would be Calc 3. Okay, Calc 3. Calculus is about limits, derivatives, and oh my. We've talked a little bit about limits. We've talked a little bit about integrals, about derivatives, but we haven't talked about integrals, and that's where we're heading today. Okay, as far as the final quest, which will be on the final exam day, which will be on the final exam slot for our class, as far as the final quest, I will not put any of the homework kind of questions related to max-min problems. Those will show up in a WebAssign. Okay, so that's the way I'm going to test you on that. The theory related to max-min is certainly fair game for the final quest. But as far as the application problems, they take quite a amount of time. I am only going to put those on a WebAssign, which I'll assign for this Friday. So you have what due this Friday? And you'll have one more WebAssign after that. That'll be due next Wednesday on integration. On polar integration, which we're going to head to on Friday. Today, though, we're starting our integration unit, which isn't horrible. I don't think students in general find this near as complicated as some of the other topics. But it's still messy. Because it's integration. The biggest thing I need you to get out of this is what I'm going to do today, which is to understand a Riemann sum. Because the applications are in the Riemann sum. What did I just say? Every major is requiring you to take this because it's applied to something in their course. And the applications are in the Riemann sum. I could teach a small dog to do certain integrals, like e to the x. But to actually understand how this is applied to engineering, finding total forces on something in physics, that's far harder. The heat on something in chemistry, P-chem, physical chemistry. All of these applications come back to a Riemann sum. And they'll constantly be doing this. They'll be setting a Riemann sum up, and then they'll immediately go to an integral. And I have to teach you guys not to fear that, but to embrace it. That when you see a Riemann sum, you get excited because you're going to get an integral out of it. Okay, so let's start, with Calc 1. Because how many people understand, if we can't understand Riemann sums and integrals in Calc 1, we're totally screwed in Calc 3. How many people want? Okay, so if you don't, by the end of today, you will. You'll be like, yes, okay, Dr. Warren, I totally get it now. Okay, so now it's like saying to somebody, do you want to go into the tiger's cage? And the kid's just like, well, I don't know. By the end of the day, they know they don't want to be in the tiger's cage, and that's the way you're going to be. You're going to be like double integrals, Riemann sums. You're going to be like, oh my gosh, I did not want to get into that tiger's cage. So let's go back and visit the kitty cat stage, okay? Which is related to the tiger, which is integration in one dimension. Now we are going to focus only on the right-hand sum definition of an integral. What did I just say?
Right hand. Focus on the right hand sum.
Not the general Riemann sum. Not the general Riemann sum. And so for us, in Calc 1, when we see the, can you read this? Can you read this? My first class was toasted. Can you read that? The
Integral from A to B.
Of f of x dx. Now I know you guys want to say it's equal to capital F of B minus capital F of A. And that's true with the fundamental theorem of calculus. But there's a lot of functions that don't have antiderivatives, which means you can't use the fundamental theorem of calculus. In fact, this is a little frightening. Most functions don't have antiderivatives. And so you have to approximate these with numerical methods. The simplest numerical method is a right-hand Riemann sum, and that's the way we're going to define this. Calculus is about, again, we're starting where we're ending. Calculus is about limits. This is defined in terms of the limits. It's equal to the limit as n approaches infinity. And this n sucks because it's up in a sum. It's called a right hand. What does the S stand for? What does the S stand for?
Sum.
Sum. So you know there's going to be a sum. And you hate summation notation, but it's really a gift. K equals 1 to n. Now n is going to where, guys? N is going to where? This is what makes this so hard. N is going to where? Infinity. And you're adding up n things. There's a function. There's a function. Now the thing is, it's not f of x. We're sticking in values, x sub k. There's n of these values we're plugging in. When it's 1, when it's 2, all the way up to when it's n. And then we're multiplying it by this other number we're calling delta x. How many people are familiar with this? How many people have seen this before? You're yawning, so I take that as a yes. I take that as a yes. Okay, now, we've got to explain, since this is a definition, we've got to explain who these guys are and who these guys are. Everybody else is fine. We've got a function, we're adding this up, and it's going to infinity. That doesn't seem so fine. But we don't know who delta x is, and we don't know who x sub k is. So where delta x is equal to b minus a, this number minus this number, divided by the n, the thing we're going to let go to infinity. Now what we notice is, since b is fixed and a is fixed, what did I just say?
B is fixed. B is fixed and A is fixed.
And n is going to go to infinity. Where's delta x going to go? If b is fixed, a is fixed, where's delta x going to go if it's b minus a over n? Where's that going to go? What number is that going to go to?
0.
0. That seems disappointing. And we don't know who these x sub k's are. And we don't know who these x sub k's are. And so we've got to define them. And where these x sub k's, for each value of k between 1 and n, is equal to a, this number, plus k is going from 1 to n, times delta x. And this is for k equals 0 through n. And this is for k equals 0 through n. Now you guys feared this, and you shouldn't. This is where the applications are. How many people understand, though, if we can't understand the right-hand sum for n equals 4, we're toasted for n equals n? How many people understand? If we can't understand it for n equals 4, then we're done. We're done. And if we can't understand it in one dimension, we're certainly not going to understand it when we go to two-dimensional integrals over an arbitrary domain of a two-dimensional function. This is the tiger's cage. This is the tiger's cage. How many people want to play with the damn cat for a while? How many people want to play with the kitty cat for a little bit? Okay, so let's go back. Oh, I just erased my limit. I'll have to put that back in there. Let's go back and unpack this for n equals 4. Because if we can understand it for n equals 4, we're done. Well, then delta x would be equal to, in this case, if n is 4, then delta x would be equal to n is
B minus A over 4.
good, thank you, Gordon. B minus a over 4. X sub k is equal to a plus k times delta x for k equals 0 through, now n is, we just picked n to be 4. So now, let's see, x0. Let's start when k is 0. Well, then x0 would be equal to a plus 0 times delta x. Well, what's 0 times delta x? 0. So this would just be equal to a. How many people are following? Then x1, the next value after the dot, x1 would be a plus 1 delta x. So it's like we moved over 1 delta x. x2 would be equal to a plus
2
delta x. And now I'm bored. The last one, x4 would be equal to
A plus 4 delta x.
a plus 4 delta x. Okay, so now that we're unpacking this, now since you can't see, I'm going to give you a drawing assignment. For not many times in this class, but for probably the third time, give yourself an xy, the old-fashioned xy, Cartesian plane. Give yourself a function. We need an f, so give yourself an f. Draw yourself an old-fashioned function. Make sure it passes the vertical line test. Now, if we look at these x sub k's, x0 is equal to a, and we're plugging that into the function. That's going in there. x0 is going in there. x1 is going to go in there. x2 is going to go in there. So a should be related to which axis that you just drew? The x-axis or the y-axis?
The x-axis.
So mark A and B on that x-axis. You've given yourself a function, then mark that down in the domain. That's the part of the domain we're going to be interested in between A and B. Now let's look at the delta x. The numerator is b minus a, which is the length of that interval you just marked. So put your fingers down. Mark your fingers. Put your fingers down on that interval that you just drew, that b minus a, down in the domain. Now you're going to chop that into how many pieces? 4. So now go ahead and do that. Chop that domain, b minus a, into 4 equal pieces. Now the length of each of those pieces is, the length of each of those 4 pieces is my delta x. So mark them. Mark all 4 of them. Mark all 4 of them as delta x. Okay, how many people are following so far? How many people are with me? How many people are still in the game? Okay, now let's look at this guy. These are the next guys I need. x0 is equal to a. So underneath a, mark that as x0. Now x1 is the point down in the domain. That's 1 delta x up from a. So mark that. x1 is the point that's just up one of those delta x's from A. X2's two of the delta x's from A. X3, you get it, and X4. So mark the points X0 through X4. Okay, now let's look at this. You guys don't like this notation, but it would be the sum of k equals 1 to who's in? 4 of f of x sub k times delta x. So write that down and write that out in a way that an 8th grader would understand it. Probably not, but pretend you'll understand it. If you're looking at the sum of k equals 1 to 4 of f of x sub k times delta x, write that, expand that out without the summation sign. Nick, I feel like you're on a spaceship. I'm digging those blue lights. I feel like you're up on a spaceship. Okay, what's the first term in the sum? What's the first term in the sum?
F of x sub 0 times delta k.
And even though the zero is there, we're really starting at 1. So it'd be f of x sub 1 times the delta x. And then what's the next term?
Sub 2 delta.
And you're like, Dr. Warren, we're bored. Okay, plus dot, dot, dot. What's the last term? What's the last term? We're bored. What's the last term?
F sub 4
Next.
delta x.
F of x sub 4 times delta x. So we need these values. I don't know why I'm yelling. Can you guys hear me okay? I guess that's part of it. Can you guys hear me?
Yeah, I can hear you fine.
Can you see the board kind of okay?
Yeah.
See, I always feel like when I'm teaching this, I know this probably isn't politically correct, but I'm teaching like an entire classroom of Helen Kellers. That's what I feel. And like I'm trying to get you to understand Braille, okay? But it's even much harder. There's so much notation in integration, let alone double integration or triple integration. So when I was dreading this, thinking about it over break, how am I going to get them to understand Riemann sums with double integrals? And I said, well, let's start with single integrals. Now, f of x sub 1, mark f of x sub 1 on your graph. And it's better be on the y-axis. It's in the freaking range. You also need an f of x sub 2, so mark that on the y-axis. And you're like, Dr. Warren, why didn't you tell me to make my function increase or decrease? They're getting all messy. Give yourself an f of x sub 3 and an f of x sub 4. You need all of those. Okay, now I'm going to catch up. And unfortunately, I've got to erase. Well, crap. What do I erase? I guess I'll erase this. I'm going to catch up with the art project. What was the first thing I told you to do?
XY.
So I'm going to do the same thing. Draw myself an XY. Then what did I ask you to do?
Draw a function.
F.
F? I guess maybe to make it fun, I'll have it go straight up like that. Just a little better picture, I think. You're like, why didn't you tell us that, Dr. Warren? Because I don't care. Okay. And then what did I tell you to do?
AB.
AB. So here's A. And there's B. And then what did I tell you to do?
Mark the delta x's.
Yeah, chop this into half. What's n? What was the n? If you don't know this answer, then you might as well turn your video off. 4. So we chopped it into 4 pieces, which I like. It's easy to do. You cut it in half, and you cut it in half again. And then mark each of these as, mark each of those as
X.
delta x. And then I said x0 ended up being a plus 0 delta x's, so that would just be a. This point ended up being x1, and then we just kind of went across the interval. Now I'm almost caught up. Now I need to mark my f of x1s, f of x2s, f of x3s. How do I do that, guys? How do I mark an f of x1? I'm here, what do I do?
Go up.
Go up and then go
Over.
over. And so this would be like my f of x1. Then I come up and I go over. This would be like my f of x2. Are you guys following? Are you with me so far? Are you with me? Then I come up. I go over f of x3. Then I come up and go over f of x4. How many people have the drawing that I have, or have something like the drawing I have? Okay, now let's try to understand geometrically what for any n this sum represents. Well, let's look. F of x1 times delta x. Well, f of x1 is the distance from the origin to here. Delta x is this distance right here. What do you notice? What's one of the things you notice about this and that? What, Dr. Moore? The f of x1 and the delta x. What do you notice about those two lengths? I don't know, Dr. Warren. Could you show me? What do you notice about this and that? There's 35 of you.
They're proportionate.
They're proportional. They're kind of, yeah, they look kind of a little proportional. I like that. What else do you notice about those two lengths geometrically? You've got this and that. What would an 8th grader say about that? They'd be like, okay, I'm quit. I'm out, Dr. Warren. I'm not doing this. This is really important, guys. What do you notice about this and that?
They're perpendicular.
Oh, bless you, Roberto. Say that again.
They're perpendicular.
They're perpendicular. This line segment is perpendicular to that line segment. And in fact, this distance is exactly the same as that distance. And from what Roberto said, that's like a right angle there. That's a right angle down in that corner. So if I look at this f of x1 times delta x, geometrically, it's like this length times a length that's perpendicular to that. Geometrically, what does that bring us back to, guys? When you multiply lengths that are perpendicular to each other, you get area. The area of a what? The area of a what?
Rectangle.
The area of a rectangle. Draw that rectangle. Then similarly, if you look at the next term in the sum, f of x2 times delta x, that would also geometrically represent the area of a rectangle. Draw that rectangle. And in fact, draw all the rest of the remaining rectangles. Draw all the rest of the rectangles. And how many rectangles do you guys got? How many rectangles do you guys have? How many rectangles do you have? 4. And how many people have ones that look like How many people have rectangles that look like that? How many people have rectangles that look like that? Rectangles that look like this. Now, what's the area? What represents the area of that last rectangle? What represents the area of that last rectangle?
f of x 4 times delta x.
Very good, Red. F of x 4 times delta x. Now, if we look at these rectangles, notice the height is always choosing what endpoint between the two. If you look at each of these little regions, we're always picking the what endpoint to be the height.
Correct.
The right, and hence the right hand sum definition. Now we could pick the left one. We could pick any point in between, and then we get the Riemann sum. They all go to the same number as n goes to infinity. In the limit, certainly the left-hand sum doesn't equal the right-hand sum. But in the limit, as n approaches infinity, they do. Now, geometrically, I've got to ask, is 4 anywhere near infinity? Is the number 4 anywhere near infinity? If I go from 4 to 8, now I'm going to have 8 rectangles. Would I get a better approximation to the actual area under the curve down between A and B? If I go from 4 to 8, would I get a better approximation? If I did 1,000,000, which is nowhere near infinity, would I have a pretty good approximation to the actual area under the curve? Okay, and this takes us back to Calc 1. Now here's the thing that pisses us off in Calc 1. Do not mess up your drawing. Don't touch your drawing. But if the function went down like this, if the function f went down, if I look at f of x sub 3, what do I notice? If it goes down, and I look at f of x sub 3, what's notably different? If you look at f of x sub 3 now, what's notably different?
It's below the x-axis.
It's below the x-axis, which would make it what kind of a number? Which would make it what kind of a number?
Negative area.
A negative number. So what we've got to remember with the integral is it's a signed area. It's not true area. It's a signed area. It's true area as long as f is above the x-axis. But the moment it dips beneath the x-axis, it's interpreting this area as negative. This area is positive, and it's adding those two things together. How many people remember this? How many people remember this from Math 235? Now you're like, Dr. Warren, but we never do the limit as n goes to infinity. Yeah, that's because Sir Isaac Newton came up with a result called the fundamental theorem of calculus. Do you think that's an important result? I mean, if you just had to guess. It's called the what?
Fundamental.
In fact, guys, right here, if we draw this line, 1700, okay? Fundamental theorem of calculus, right here, okay? This side, ancient science. That side, modern science. Ancient science, modern science. All because of this. All because of the fundamental theorem of calculus. What Newton showed was that you can actually find this limit by just doing f of b minus f of a. You can find this limit by just taking a certain function, plugging the number b in, and plugging the number a in. Now, what's the relationship between capital F and the little f? What did you learn back in Math 235? What is the relationship between capital F and little f?
The derivative of capital F is little f.
The derivative of capital F is equal to little f. This is the fundamental theorem of calculus part 2. It changed everything. You're like, well, Dr. Warren, I'm not seeing it. Well, guys, it's not just area. I mean, sure, I gotta imagine, like, if you were at Cambridge and Newton drew some weird function, like x squared, or like, and you go, what's the area between 0 and 1 of x squared? How many people could figure that out? I mean, if I said, find the area between 0 and 1 of x squared, how many people think they have a shot at finding that? If not, you're in the wrong class, okay? But guys, back then, before Newton, they would have said that was impossible. They could find the area of rectangles. Triangles, it's really a rectangle. Trapezoid, not really two triangles, so a rectangle. And then they had circles. Other than that, nothing. Everything went back to a rectangle or a circle. And when Newton said, I can find this, let alone under sine, cosine, As a geek mathematician at Cambridge, you had your mind was just exploding, going, this is insane. Let alone the physics. How far does the planet travel as it orbits? That's impossible. If you shoot a cannonball, how far will it travel? Can we predict that? That's impossible. Not with Newton. Not with Newton. Okay, stand up, because I can tell already you're not, in 1 week you've gotten lazy in teaching shape. You have no attention span. Stand up. Put your hands on the space bar. Put your hands on the space bar. Put your hands on the space bar. Tell everybody to wake up.
Wake up.
Say, wake the hell up.
Wake the hell up.
Okay, sit back down. Okay. Now let's see if you learned anything from what I just taught you. We've got another one-dimensional Riemann sum. Unfortunately, it's not in terms of x's. It's in terms of ice cream cones. But it's still the same thing. Because if we can understand it with this, I'll be pretty confident we can go to x's and y's. I've got the limit as apple goes to infinity. The limit as apple goes to infinity of the sum of j equals 1 to apple. The sum of j equals 1 to apple. My function's not f, it's h. I'm evaluating that function h at ice cream cones sub j. And then I've got a delta, what? I'll see if you can read it. You got a delta what?
Ice cream cone.
Ice cream cone. Where delta ice cream cone is equal to sun minus banana over j. And these ice cream cones of j, you're plugging into your function h, are equal to banana plus j times delta ice cream cone for j going from 0 to apple. This limit will go to an integral. Write down that integral. The game is on. It's an escape room trick. Can you escape the room? What integral will this Riemann sum go to? The game's afoot. Okay, for sake of time, I must stop you. For sake of time, I must stop you. How many people had one of those? How many people had an integral sign? How many people had an integral sign? Okay, now let's see. Your integral is running between where and where in the domain? Is running between where and where?
Sun.
Between banana and sun. So if you didn't write that, it's between banana and sun. How many people had banana and sun? How many people had a banana and the sun in those locations? Okay, then what did you have? How many people had an H? And H of what? H of what? H of what? Ice cream cone. How many people had that? How many people had that? And then it's D what? Then it's D what? D what?
Ice cream cone.
D ice cream cone. And so guys, I mean, this is just in one dimension, and we're going to go to higher dimensions. Listen to me. When you see stuff that looks like this, in physics, in engineering, in chemistry. You're seeing you're adding up functions evaluated at specific points, times some chunks of the domain. I want you from now on to be thinking what? When you see something like this and they're saying, oh, we're gonna make the chunks smaller, I want you to be thinking what? This is the most important part of today. When you see a sum where you got a function evaluated at discrete points times little chunks of the domain, and they're gonna let those chunks get smaller, I want you to get excited because you're beginning to see a what?
Integral.
An integral. This is the way Newton thought. He took the impossible. Say that.
Took the impossible.
Approximated it with things that were already understood by chopping up the domain. And then took the limit, went to an integral, then did the impossible with his fundamental theorem of calculus. That's the circle. That's the circle. The circle of academic mathematical life is this, as far as calculus is concerned. You have a physical application that's impossible. You approximate it with things that are possible, as long as there's a limiting procedure. That sum goes to an integral. We evaluate that integral with, we've already forgotten. We've evaluated that integral with,
Limit.
the fundamental theorem of calculus, avoiding the Riemann sum and the limit. We use what I erased, the capital F of B minus capital F of A, to do the impossible. Listen, there's so many applications for this, guys. There's so many applications. Physical problem, impossible. Approximate it with something that's possible. Write it as a Riemann sum. In the limit, it goes to the thing. Impossible to do the Riemann sum. It goes to an integral. Evaluate the integral with and you've done the impossible. You've done the impossible. So yeah, we'll just stop with that. We'll just stop with that because this is not Calc 1. This is not Calc 1. This is Calc 3. Let's go play with the tiger. Let's go play with the tiger. Okay, first of all, draw yourself an X, Y, Z. And I'll do the same. Now let's give ourselves a function. Except now it's not one-dimensional, it's two-dimensional. When I say z equals f of xy, you say, when I say z equals f of xy, you say,
Space sheet.
space sheet. Draw yourself a space sheet. And I'll do the same. So I've got myself a space sheet. My domain's down here on the floor. My domain's down here in the XY plane. And the first thing that we notice is that a chunk of the domain was so simple in one dimension. That's about as much as you can get, an interval between A and B. But down here on the ground, a chunk of the domain could look like a kidney-shaped pool. It can be any shape we want. In fact, we can mark that as something that scares kids called omega, not omega. And then we can talk about the double integral over omega of the function xy. The double integral over omega of the function xy. Now math is
Proof.
proof. Right now, we're not going to talk about omega. How many people understand if we can't understand the double integral for a rectangle, if we can't understand where omega is not the shape of a kidney-shaped pool, but a shape of the pools popular in the 1940s, which were rectangles, we're screwed when we go to ponds. How many people understand that? How many people are with me? So all the rest of today is going to be talking about how to do the double integral, over a rectangle, where this thing is a rectangle. Now I'm going to give you something. I'm going to start you off. I'm not done with my drawing. I'm going to show you geometrically what this integral represents. Instead of representing area, when we jump up a dimension, it would represent, geometrically, it would represent. Instead of representing area, geometrically, when we jump up, it would represent volume. It's the volume under my space sheet, down here, over my domain omega. And so what would happen is, we would take every single point on the outside, just kind of like what we did here. We went up from A, hit the domain, hit the function, here, and then we looked at the area under that. The problem is now, the outside, there's a lot more points. So we come up, hit, take another point, come up, hit, take this point up, hit, this point, and this is going to be a little bit messy as I try to draw this out. Looks like we're swinging down, swinging around, and we're definitely swinging up. And so we're looking at something. I need to come out here a little bit more. We're looking at the volume under between here and here. We're looking at the volume of this chunk, where these go straight up and hitting my space sheet. This goes straight up, hitting my space sheet. So now what I want you guys to do is do the same thing. Draw an XYZ. Start again, drawing an XYZ. Give yourself a space sheet. Z equals f of xy. And I'll do the same thing, because I want it drawn a certain way.
I have a question, Dr. Warren.
Yep.
So, like, omega, you know how, like, in XY plane, you have A to B, so is that the same with omega? It's like that?
You know, Raylan, it is. It's an extension of that, and that's what our first extra complication is. It's not just an interval like what we're thinking of. It can be any chunk of this domain, as long as it's nice and connected. Like, it could have a warp coming off of it here, and then that's going to extend up into here, something up there. So it's far more complicated.
Okay, thank you.
No, thank you. It's going to get a little bit easier because we're not going to work with a warded kidney-shaped pool. We're going to work with a rectangle. So let's come down here and let's draw a rectangle, because we're screwed if we can't understand it for a rectangle. Now we're in 3 dimensions. We're drawing here, so it's not going to look like a rectangle. I'll make this more parallel. My one side of my rectangle is going to run parallel to my x-axis. The other side of my rectangle is going to run parallel to my y-axis. So this is my rectangle. Now the rectangle is a lot easier to describe than a pond. We can actually use some of the stuff that we were doing before. We can say all the x coordinates in the rectangle are bigger than A, but less than b. All of the points in here, their x coordinates bigger than a, but less than b. So if I think of a point x, y in my rectangle, the x coordinates in between these 2 points, and because I'm not being clever, my y coordinates are running between 2 other points that I'll mark as C and D. So x is going between, can you read this? X is going between,
A and B,
and y is going to run between
C and D.
C and D. So let's at least mark this thing. Let's call this rectangle R, for in lack of anything clever. Capital R. And then let's come over here, and then we can talk about R. Now remember, guys, this is not the integral. This is not the integral. This is just the domain. R is equal to the set of all the points x, y, such that x is greater than or equal to A and less than or equal to B. And y is, you guys help me out, I'll see if you're focused at all. Y is
Greater than or equal
Equal
to
to
C,
C. What's that?
and less than that, or
equal to D, less than or equal to D. Okay, stand up. You're going to need to stand up. We're going to define the integral for this. So stand up. You're not going to like it. Stand up, stand up, stand up. You just told yourself to wake up. You better listen now. You better, Robert, you better be up. You better be up. Ava, you better be up. You better be listening. Hunter, you better be up. Okay, sit back down. Now, here we go. The double integral over the rectangle R of the function f of xy dx dy is equal to not shocking that it be defined in terms of a limit. It's not shocking that it would be defined in terms of a limit. It's a two-dimensional space sheet, which sadly means it's going to be a two-dimensional limit. You're going to have an M and an N. An M and an N. And it's going to go to infinity, infinity. It's a two-dimensional limit as M goes to infinity and n goes to infinity. We have not a single sum, but a double sum. Not a single sum, but a double sum. The inner sum is going to be k going from 1 to n. K going from 1 to n. The outer sum is going to be j going from 1 to m. So we have the limit as mn goes to infinity, infinity. The sum of j equals 1 to m. The sum of k equals 1 to n of f of x sub k y sub j times delta x times delta y. This is our right-hand sum. This is our right-hand sum definition of an integral over a rectangle. But you say, wait, Dr. Warren. No, you don't. You didn't say this at all. And most of you wouldn't even care. You say, wait, Dr. Warren, this is a definition. Who is this delta x? And who is this delta y you speak of? Who are these x sub k's? Who are these y sub j's you speak of? Well, I'm glad you asked. I'm glad you asked. So ask me.
What are these X and Y's and?
Yeah, X and Y's and J's, oh my. Who is this?
Okay.
And,
Delta Y.
and, I know it's hard to see,
X of K.
X and K,
and
Y sub J.
so let's define these. You're like, no, Dr. Warren, let's not define them. No, let's define them. Where delta X is equal to, if there was any mercy in this class, what would delta X be equal to?
Minus A over N.
Thank you, Raylan. Raylan's the one person who's like, yes, it would be awfully nice if that didn't change. Okay, now let's take Raylan's lead. Then who would delta Y be equal to? What would you guess? Extrapolate. What do you think delta Y would be equal to?
D minus C
C
over
minus
M.
C over M.
D minus C over M. How many people are following? How many people are with me? How many people are with me so far? Now, let's talk about this guy, the X sub K's. Let's talk about the X sub K's. Well, remember in our one-dimensional version, X sub K was equal to what? You can even go back and cheat. X sub K was equal to what?
A plus delta X.
A plus K delta X. So let's do the same thing. For K equals 0 to N. Now we're almost done. We only need one other person to identify here our Y sub J's. What do you think our Y sub J's are going to be equal to? Extrapolate from what we just had. What do you think our Y sub J's are going to be equal to?
C plus J.
C plus J delta Y as J goes from 0 not to N but to M. And you're like, Dr. Warren, that's a nightmare, man. That's a nightmare. Look at all that notation. I was thinking about, I'm going to be teaching the kids on the grid this. They're not going to be able to see my notation. How am I going to do this? But fortunately, I'm making an iPad video. I've got to ask guys, was it any use breaking down that one-dimensional into 4 pieces? Did that help you at all, at least understand it geometrically? Was that useful at all?
It was a good refresher too.
Good refresher too. Okay, well, would it be useful if we did the same kind of thing for the 2-dimensional? Would it be useful? Now here's the thing, guys. It's not a single sum. It's not a single sum. It's a
Double sum.
double sum. And notice, there's an N and there's an N and there's a M. And they're not running at the same rate. M could be a different number than N. So I'm not going to pick 4, because both of them wouldn't have to be 4. I'm going to make it as easy on Dr. Warren as possible and still have it teachable. I'm going to choose M to be 3. I'm going to choose M to be 3 and N to be 2. Because if we can't understand it for 3 and 2, we're done. We're done in general. So now what I'm going to come over here and do is I'm going to erase my pond, my general integral, and I'm just going to look at this thing that nobody understands at the moment. I'm just going to look at that, and I said M was going to be what? I said M was going to be what?
3.
And N was going to be
2.
2. So let's come over here. We're looking at the sum of J equals 1, 2, 3. K equals 1 to 2 of f of x sub k, y sub j, delta x delta y. So, because if I can't understand this, then we're done anyhow. Okay, now delta x was equal to b minus a over, now you look over there at our definition. Delta x is equal to b minus a over what in this case?
N.
And who did we pick n to be? Who's the n? Who is the n, guys?
2.
2. So we're chopping the domain between A and B into 2 pieces. So in your drawing, do that. In your drawing, break that into 2 pieces. And mark the length of each of the pieces on the x-axis as delta x. Mark. My drawing may not be big enough, but we'll see. So I'll do the same thing. We're chopping this domain into 2 pieces. Each of them have length delta x. How many people are following? How many people are with me so far? Okay, my delta y is equal to d minus c over m, but who's m? Who's m?
3.
3. So this would be d minus c over 3. So we're chopping that interval on the y-axis into how many pieces? So do that. Chop that interval between d and c into 3 pieces and mark each of the pieces as delta y. And I'll do the same thing. Okay, x0. x0 is equal to a plus 0 delta x's. So that would make this guy right here, that would make this guy x0. This guy's x0. x1 is equal to a plus 1 delta x, and x2 is equal to a plus 2 delta x. So mark your x2 and mark your x1 on the drawing. Mark your x2 and mark your x1 on the drawing. And then similarly, mark your y0, y1, y2, and y3. Mark your y0, y1, y2, and y3. And I'll do the same thing. This is my x1. That's my x2, since I'm just using 2 intervals. And I know this is when it's good I can see your faces. I can tell some of you are still drawing, so. So I've got x0, x1, and x2, because we just used 2. Here we did 3, so I've got my y0, y1, y2, y3. Now, how many people are following so far? How many people are with me? Now, back in one dimension, it was really easy. We had our A and our B. We chopped it into 4 pieces. All of them were delta x. Here was our x0, x1, x2, x3, x4. And this chunked my domain. This brought my domain into 4 pieces. This is much harder. This is my domain. But this has actually divided my domain up. You know, nobody has it, Dr. Warren. It really has. If you just extend these lines and extend these lines, the ones that are parallel to the x-axis and the ones that are parallel to the y-axis, we see that chopping the x up into 2, chopping the y up into 3, has actually chopped our domain up into 6 pieces. Do you guys see that? Do you see how this has naturally chopped our domain into 6 pieces? Now come back over here. Imagine that m was 10 and n was 5. How many pieces would we have? If m is 10 and n is 5, how many pieces would we have our rectangle chopped up into? 50. Now here's the kicker. N's going to freaking where? N's going to freaking where?
Infinity.
M's going to where? Infinity. We're like, okay, Dr. Warren, I'm barely hanging on with 3 and 2. I'm barely hanging on with 6. Okay, now I'm going to pick some points and I want you to label them. Dr. Warren, what are you talking about? I'm down here in the domain. I'm going to pick some points and I want you to label them. What is the coordinates of that corner point of that rectangle? What are the coordinates in terms of your x sub k's and y sub j's? What are the coordinates of that corner point?
X sub 2, y sub 3.
X sub 2, y sub 3. I don't want to get our drawing too messed up. So I'm also going to pick that point right there. I'm going to pick that point right there. Label that point. What are the coordinates of that point right there? Anyone? What are the coordinates of that point, if you can see it?
X sub 1, y sub 2.
X sub 1, y sub 2. So mark it as such. You're not going to see it in my drawing. I know you won't be able to see it. X sub 1, y sub 2. Okay, how many people are following so far? Now you're not going to follow. Oh, great, Dr. Warren. That's what I want to hear. Now you're not going to follow. We've got to actually unpack, for the first time, unless you've done computer science, a double Riemann sum. We've got to unpack a double Riemann sum. What's hiding here? What's hiding here is that there's actually an order to this. We first of all do the sum in terms of k, and then we do the sum in terms of j. So let's do this. I would have the sum of j equals 1 to 3. Yeah, I guess I'll write it like this. Now let's ignore this sum. Let's ignore this sum. Let's look at the inner sum. I would have the sum of k equals
1
to 2. Now, where else? All I need to worry about is where there's a k. Is there any k with this guy? Is there any k with that guy? Is there any k with that guy? Is there any k with that guy? Is there any k with this guy? Well, you're like, the only explicit expression with k is the x sub k right there. This is a y sub j, this is an x sub k. So let's write this out. It would be, first of all, I'd start with a 1. So I'd have f of x sub 1, y sub j, delta x, delta y. That's the first term in my sum. Plus, what's the only other value of k we need to worry about for this simple example? What's the only other value of k we need to worry about?
2.
2. So then I would have an f of x sub 2, y sub j, an f of x sub 2, y sub j, times delta x, delta y. So we've unpacked that inner sum. We've unpacked that inner sum. Are we done? Are we done? And the answer is no. We now have to unpack the outer sum. I'm going to do it with the outer sum. The outer sum's running on j. Dr. Warren, I'm not listening to a word you say. The outer sum is running on the subscript j.
J.
I am your German teacher now. You will pay attention. The outer sum is running on j. Sorry, everything I do is probably politically incorrect. I'm old. I'm 60. The only place I see a j is here and here after unpacking that inner sum. So now, wherever I see the j, I'm going to start putting my indices 1, 2, and 3. First of all, it's going to be a 1. So I would have f of x1, y1, delta x, delta y. Plus the f of x2, that's not changing, y1, delta x, delta y. Am I done? No, I still need to do plus, because that's what that means, sum We finished with 1, now we're gonna go to, we finished with 1, now we're gonna go to 2, and then we're gonna go to 3. And you guys are gonna do that, not me. You guys are gonna finish that rest, unpacking that. You're gonna finish unpacking that with the indice 2 and the indice 3. Because it'll be easier for you to think and write it down than to try to write what I'm writing and not see. For sake of time, guys, sorry, for sake of time. What do you have here? What do you have as your first one? What do you have? 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 What do you have?
F of x, y1, or x1, y2.
Awesome. F of x1, y2 times
Delta x delta y.
plus
F of x2, y2 times delta x, delta y.
Okay, and then our last subscript is going to be 3. You're going to have f of x1, y1, y3, delta x, delta y, plus f of x2, y3, delta x, delta y. How many people had that? How many people had that? How many people were at that point? So how many terms are there in my sum once I've unpacked everything? How many terms do I have in my sum? 6. Okay. Let's just try to geometrically understand one of them. Let's just geometrically going to try to understand one of them. Let's look at just this term right there. Let's just look at this term. Because if we can't understand it for one term, we're not going to understand it for all of the 6 of them. And if we can't understand it for 6, we're sure as hell not going to be able to go as m and n goes to infinity. Now you guys help me out. This one in particular is what? Read that to me. Read that to me through its blurriness, or read it to me on your sheet. What is that?
F of x1,
y2.
Y2 times
Delta x, delta y.
delta x, delta y. Now, go back and look at your diagram. Go back and look at your diagram. Let's see what delta x is. Let's just look at delta x. Delta x was this distance here. It's where we chopped our domain into 2 pieces on that x-axis. Delta y is this distance where we chopped it there. The point in the domain we're interested at, we've already marked. It's on that point right there. You've already marked it down in your drawing as x1, y2. You've already marked that point in the domain. Now let's think about delta x times delta y. That's in this term. Well, what's the distance? If I look at this little rectangle right here, where this is kind of like the right-hand endpoint. Right hand in x, right hand in y. What's the area of that little rectangle? What's the area of it?
Delta x times delta y.
Do you guys see that? How many people see that as delta x times delta y? So this would be delta x. This is delta y. So we at least know this piece. We know that that piece right there is in fact the area of this rectangle. Let's look at the other piece. It's f of x1, y2. Well, that means we're using our space sheet. That means we're using our space sheet. How would I evaluate? How do I find f of x1, y2? What do you do, guys? You go straight, take the elevator straight up until you hit your space sheet, and then you go over to the, help me out, I've been teaching you this all semester. Then you go over to the
Z-axis.
it's z equals. So we come over here on the z-axis, I'm kind of imagining it's going like this, and this is f of x1, y2. Okay, I want to draw a parallel. I want to draw a parallel back to the one-dimensional case. Remember we did this, we had this, we chopped our domain up into 4 pieces. But if I looked here, maybe this was x2. This was f of x2. It was over here in the range on my y-axis. This is f of x2. But we looked at this rectangle right here. Its area was delta x times f of x2. This height was the same as that height. That's what we used. But if I look here, this is f of x1, y2. It's this distance. But I've got to ask, is this distance not the same thing as this corner over here that I have right there? Is that distance not the same thing? And I'm contorted in a way that somebody better say yes, or I'm going to like maybe be permanently left like
Yes.
Yes, this is the same thing. This distance here is also f of x1, y2. Now I've got area, delta x, delta y, times height, f of x1, y2. But length times width times height is volume. The volume of what geometrical shape?
Rectangle.
A rectangular prism. Good, Stuart. Nice. A rectangular prism. Well, I don't know if that was Stuart or not. Stuart, I gave you credit. That poor guy behind you, Stuart, he's like, what the hell class is this? A box. Now let's try to draw that box. Let's try to draw that box. Either I would go straight up, then I'm going to go straight over, then I'm going to go straight down. Then I've got another corner that's going like this, and now we're flat. We're flat. Parallel. We're flat, parallel to the ground on the top. And the volume of this box, is height, f of x1, y2, length, delta, well, we'll call width delta x, and length delta y. Do you guys see geometrically what this term is? Do you see geometrically what this term is? Can you guys visualize that now geometrically? Now imagine we did this. Imagine we did this for all of these. Imagine that we did these for all of these. I'm just going to do one more. Let's look at this one. Let's look at this one. We got f of x2, y3. f of x2, y3, delta x, delta y. This term, this last term, this other point that we have. You guys try to draw the box that would represent the volume of that part of the Riemann sum. You guys try to draw the box that would represent that part of the Riemann sum. Okay, I'm hoping that you guys drew something like this. You have your delta x, delta y, your corner point's going to come up. Well, I guess maybe a little hard to draw in my drawing here. come out, we're going straight up, hitting my space sheet right about there, kind of going over, running along here. Sorry, I gave you guys an impossible drawing assignment. I gave you guys impossible. How many people's boxes was at least shorter than the other box? How many people had a box that was shorter than the other box? Fortunately, this is not art. Fortunately, this is not art. Now, how many sums did we have? How many sums did we have, guys? How many sums did we have? 6. Imagine that we did this. Imagine that we did this for all 6 of them. Do you see how we would get an approximation to a shape that might, the volume of a shape that might look something like this? Do you see how, like, if we did that, we would get an approximation to a shape? Here's the rectangle. Here's my space sheet. I've got this edge running along the space sheet, this running along the space sheet. These are going straight over, and then I'm going straight down. Okay, now imagine before Newton somebody said, what's the volume of that? What would the answer be? What's the volume of that, Newton asked. And what would have they said back in the 1700s? That's
Impossible.
impossible. Okay, on Wednesday, we're going to make the impossible possible. Okay, I'm going to assign what that's going to be due on Friday.
WebAssign.
WebAssign, related to Max Men's, I hope you guys had a wonderful break. I hope you had a wonderful break. We want to vomit on the right side of the finish line. Do not vomit before you cross the finish line. You know you're going to vomit. Vomit after you finish the race. Okay, that's my wisdom for the day. That's my wisdom for the day. Wisdom from Dr. Warren. I will see you on Wednesday. Thanks for coming. Thanks for coming. Thanks for playing.
Have a good one, Dr. Warren.
See you guys.
Thanks for class. Thank
Go,
you.
Dr. Warren.
Have a good day, Doctor.
Aw, thanks, guys. Whew. See, it looks so clear there, and yet I know they can't see.